Thank you very much for the nice introduction. So I'm Pedro. I'm a PhD student at the KU Leuven and GE Vingmet in Norway. And I'm here today to talk about high frame rate 3D TDI. And the motivation for this work is the same as most of you in this room. We want to go faster. And we want to go faster because that would allow us new applications. For instance, activation imaging. And luckily, there has been lots of work in this field, and we have nowadays multiple options to increase temporal resolution. And for instance, we know that in 3D, if we use diverging waves, we can achieve very high frame rate. However, this has been implemented on research systems which use fully wired probes. On the other hand, clinical systems, they make use of sub-aperture beamforming, which seems to be challenging to combine with diverging waves, as we'll see in a minute. So the aim of this work was to propose a 3D TVI fast acquisition sequence using diverging waves on a beamforming system, on a sub-aperture beamforming system. And we want then to validate it by implementing in a clinical scanner. And because my PhD is mainly focused on electrophysiology procedures, I'll be using a transesophageal array, but the same conclusions would apply to a transthoracic one. Okay, so why do we need sub-aperture processing? So we know that when we go from 1D array to 2D array, we have a large increase in the number of elements. So if we would like to keep all the elements connected individually to the system, we would need a very thick cable. But that would be very costly to produce and also very impractical to use. So what the clinical systems use is a sub-aperture beamforming, which is a two-stage beamformer split between the probe and the system. And the way it works is that the incoming echoes, they are pre-beamformed for a set of neighboring elements called a sub-aperture. So they are steered according to a given focal point, and then they are summed into a single channel. These channels are then passed to the second stage of the beamforming, which happens in the system, and where dynamic receive beamforming can be applied. But we see that for each SAP, we get a single channel, and this way we can reduce the number of channels that we need to communicate between the probe and the system. So a particular example, if we want to reconstruct this line in orange, we would have our array with a big number of elements. We would combine them into sub-apertures, pre-steer them according to a given focal point, in this case this yellow star, and then we pass these channels to the system, and in the system we can delay them as usual according to the receive line we want to reconstruct. And we see that these SAPs, which are in color, align pretty well with a theoretical delay in black. And therefore, we have a very nice beam profile. Now, the challenge with diverging waves is that we want to reconstruct a variety of receive lines which have very different orientations. So in this case, we also want to reconstruct this line in orange. And so again, we start with a system, lots of elements. We pre-steer them. But now we have to remember that this is the same transmit event, and that's the purpose, that we reconstruct multiple lines from the same event. So these elements were already pre-steered in the first case. They have the same focal point for the SAPs. And then we pass them to the system, and there we can again delay these channels according to the desired direction. And what we see is that the SAPs align with the theoretical delays, or at least the SAP centers. But then they have been pre-steered in a non-optimal way. So what we end up is a main lobe in the desired direction, but we also get energy from a secondary direction, which is called the grating lobes. So in order to study this a bit more systematically, we have designed a simulation study where we have used 4 transducer configurations. So we go from the fully wired array where each element can be controlled individually, and then we combine neighboring elements into sub-apertures. So in this case, 3 by 3 elements, 4 by 4, 6 by 6. And by combining more elements, we of course reduce the channel count. So we have less colors, meaning less SAPs that we need to interface with the system. We have then designed 3 scan sequences going from a very broad diverging wave covering the whole field of view, and then some sparse transmit acquisitions where we divided our image into subsectors, and then we have multiple diverging waves, each one covering one of these subsectors. So we want to study this effect of steering. We have then designed the imaging phantom, which consists of a sphere rotating, from which we can then reconstruct velocities. And the sphere is then surrounded by static scatters. And we have used field 2 for the simulations. So the structure of the results will be similar in the following slides. So on top, we have the different sub-configurations. So starting from the fully wired array, and then a 3x3 sub, 4x4, 6x6, and you can see that by increasing the number of elements we combine, we can reduce the number of channels required. And then here we have the different transmit schemes, so a broad diverging wave and then sparse transmit schemes. So what we see is for a fully wired array, as we would expect, we can scan our field of view without grating lobes, so we get just the main lobe, so all the energy will be coming from there. But as soon as we introduce the SAPS, then the case changes. So what we see here, for instance, this extreme case, where we require the system to steer much more on the second stage of the beamforming, because we have a single focal point for the SAPS, and then we want to reconstruct all the lines in the system. And what we see is that we have our main lobe, but we also have a quite strong grating lobe. And sometimes the grating lobe is even higher than the main lobe. So this is the extreme case. As we go towards these scenarios where we have smaller diverging waves, so we don't require as much steering on the second stage. And also as we have smaller SAPs, we start to go towards the reference case. So in this case, we see much less grating lobes, so we expect a much better image. So this also reflects on the beam mode images. So again, for the case of single diverging waves and big SAPs, we see a degradation of image quality. We don't see this cyst anymore in this case. And as we move towards this direction, we are able to improve image quality, and we can get very competitive images, especially in this region, where we have moderate SAP sizes and moderate diverging wave opening. So we want to do TVI, so we have then plotted the tissue velocity maps, and we see the same effect. So here again, it's quite clear that we have grating lobes. So for instance, in this region, we would expect a negative velocity, so blue, and what we see is red. And the reason is, when we want to reconstruct this line, our grating lobe will be here, and will be stronger than our main lobe. So our energy will be coming mostly from this direction, which has a positive velocity. So what we see is that we have a strong bias on our velocities, and we also see, especially in these cases, some underestimation. As we can see, we don't get these higher velocities up here. And then again, in this case, with a 2x2 diverging wave, we can improve the results. We still see some lower sensitivity for this case, some grating lobes for these extreme directions. As we can see here, we pick some velocities, blue and red. And then as we go to a more contained diverging waves, our velocities seem to agree more with the reference case, which is, again, the fully wired array. So if instead of just looking at 2D slices, if we compute the velocity error for the full 3D volume, so remember we have a sphere, we see the same pattern again. Single diverging wave, much bigger errors, considerable underestimation of the velocities, and this tends to improve as we narrow down our diverging waves. And for each scanning sequence, we see that the bigger the SAPs, the bigger the error, which would be expected. So we have then tried to validate these results in vivo. So we have implemented it in a clinical system, in this case the VVD95. We have used a transesophageal array, and we have performed the parasternal long axis view. So here I would like to point that this was a transthoracic acquisition just for the ease of acquisition. This was also done by a non-experienced examiner, meaning self-scanning. And then we have recorded B mode and TVI. In this case, I'm just showing again to this slice. And what's interesting is that if we look at the velocity curves and we compare the conventional case where we have focus beams to the case I've just shown with 3 diverging waves, which seems from the simulation results to be the best scan sequence, we can see that the velocity curves, both on the septal wall and also on the posterior wall, they seem to agree quite nicely. So we retain the same waveform. We seem to retain the same peak velocities as well. So this seems to indicate that we can increase frame rate significantly. So in this case, because we were using a clinical system, we used also a clinical TVI scan sequence, meaning that we have packets on our acquisition. So that's why we have this kind of frame rates. If we are then able to do a continuous Doppler processing, meaning frame to frame, we should be able to get up to 600 frames per second in 3D. So in this case, for the 2D slice, we achieved 360 compared with the 43 in the focus beam, and still retaining all the interesting velocity relations. So to conclude, our simulation study resulted in the fact that it doesn't seem feasible to perform a single diverging wave on a system with sub-apertures, because we'll get grating globes from the SAPS, which are limited on the pre-steering. So we have one pre-steering direction, but then we want to reconstruct multiple lines. However, it seems that a sparse sequence, for instance, with 9 diverging waves would lead to acceptable results and still retaining high frame rate, so in this case 600 frames per second. We have done then the in vivo study where the focused beams and diverging beams, they seem to lead to the similar velocity curves, although we still have some challenges, for instance, reduced penetration with diverging waves. And so for future work, we would like then to implement a continuous Doppler processing so that we could avoid packets and then increase frame rate. And then we would like, instead of a 2D slice, we would like to show some 3D visualization technique, maybe some activation mapping, and we need some more in vivo validation, for instance, with animal cells.